Our next speaker is James Reid from Mirror Geoscience. James is going to be talking on 3D data integration and analysis. James obtained his PhD in geophysics from Macquarie University in 2000 and lectured in geophysics at the University of Tasmania before moving to Perth in 2006. He has since worked for several data acquisition and consulting companies and is currently a principal consultant and director, Asia Pacific at Mirror Geoscience. He has broad experience in geophysical techniques, specialising in electromagnetic methods. He also has considerable expertise in 3D visualisation, integration and interpretation of multidisciplinary data, obtained through consulting work and collaboration with software development teams at Mirror Geoscience. He was president of the Australian Society of Exploration Geophysicists in 2006-07. He is principal or co-author of 4 papers which have been awarded Best Paper at ASEG AEGC conferences in the fields including mineral exploration, coal and geotechnical geophysics. Please welcome James.
Thanks, Donna. You all hear me okay? Yeah. Look, I'd just like to firstly say thank you to the AIG for the invitation. Look, as a white-haired, bearded individual, I'm usually in the majority at some one of these things, but today I'm forming my own cluster of one, I think. So it's good to see, so many early career people here. I'm just going to turn this notification off. So I'll be talking today about data integration and analysis in 3D. And a brief outline of the talk. I've got a couple of disclaimers. I'll be talking about why we want to visualize things in 3D, some fundamentals of software, some obstacles to 3D visualization of geoscientific data, a few examples of different kinds of visualization and ways that we can analyze data in 3D. And I'll be talking about the concept of the Common Earth model and integrated interpretation, which is very important. And then I have just one case history from Cave Rocks, which is a nickel exploration case history. And instead of the second case history on the Jaguar BHMS deposits, I'm going to just do a quick demonstration of 3D visualization, just a few minutes. And then some conclusions. So my first disclaimer is that, as Donna mentioned in the introduction, I'm employed by a company that develops 3D visualization software and geological modeling software, and that is GeoCAD and Geoscience Analyst. So just, the examples I'm going to show are from our own software. Disclaimer 2 is, as Donna also mentioned, I'm a geophysicist, so I will be touching on geological topics today, but, if you haven't seen this cartoon now, I'm filling a very large gap in your education, all right? Because it's very, very, very relevant. So why do we want to go to 3D? Geoscientific data is fundamentally 3D, and some kinds are even 4D, which means they have a time dependence. So hydrogeological data, geotechnical data where they're constantly developing mines and things like that, and conditions are changing underground, is a 4D situation. You're throwing away information when you display 3D data in 2D. And a classic example of that is just magnetic imagery from geophysics, where a magnetic image like the one at the top right contains some very, very shallow features. So these things striking northwest in this image are, in fact, they're just sand dunes. They're right on the surface. They're barely underground. And you've got some deeper things like this great big anomaly here, which is clearly at some depth. So if you just get your magnetic image and draw a few lines on it, you're throwing away the 3D information that's available in that data. And I should say, by 3D here, I mean visualization and integration of data. When you're working around active mines, either in mine or near mine exploration, then they acquire a lot of new data over the years, and they often just interpret those surveys piecemeal as they come in and never really fully go back and integrate them with the rest of the information that they have available. So, we have had clients who have had operating mines for 30 years who had never seen all their data together in a single 3D visualization. And I remember one guy saying, "Oh, what's that?" And I said, "Well, that's data you acquired 20 years ago that you've never seen together with all your other data." So, you know, how are you supposed to make the most of your data if you can't visualize it all together? And to get the most from all your exploration data, and that's geology, geochemistry, and geophysics, plus whatever else, you need to be able to visualize it in a common environment and interpret it with a multidisciplinary team who understand the data that they're looking at and can get the most out of it. I can't emphasize how important that is, and I'll say that again several times during this talk. So some fundamentals about software. Many of the software packages that we currently use have very long development histories that go back, you know, often to the 80s or sometimes even slightly before that. And that the 80s was when computing power reached a point where you could even contemplate this sort of thing on a desktop computer. They were often, you know, from the outset, they were designed to visualize 2D data because that's really all that was possible. And that could be 2D plan or section data. And then over the years, 3D visualization has been cobbled onto those software packages as an afterthought, right, or later in development. But in the last 10 to 20 years, software explicitly designed for 3D visualization has become widely available. And some of it is, you know, you can go anywhere from the very inexpensive to, or free, to extremely expensive, depending on, you know, what bells and whistles you actually want. And as I'll say many times in this talk, the ability to compile and visualize your multidisciplinary data in 3D can provide huge interpretational advantages. And this slide or image on the right is just a gratuitous attempt to put as many 3D objects in a single view as was humanly possible, even though, you know, could have put some more things in there, but it's, I wouldn't be sort of looking at a view like that normally and trying to make sense of it. What are the obstacles to 3D visualization? We have very big data sets. That's the primary one. If you're in a mature mining area where there's been exploration for 50 plus years, I've seen several projects with more than 100,000 drill holes. So you're looking at huge amounts of data. It's very difficult to handle in, you know, in a sort of real-time scenario. We have other huge digital data sets like LiDAR and 3D seismic, which can be, you know, very, very, very large. You can just have spatially be looking at a very large area like regional studies, or in very high detail at a local area, and you've still got massive data sets. So this image that I'm showing you here is the entire Canning Basin, and it's sort of showing some 2D objects here. So these lines out here are seismic lines, and then the coloured ones here are airborne EM conductivity depth sections produced by Geoscience Australia. And that is 40,000 kilometres worth of airborne EM data. It's sampled every 15 metres along each one of those lines. You can see the scale bar there, 200 kilometres, sorry. It's a very large area. There are over 30 million data points in that view. I can visualize that on my laptop, spin it around. Every single one of those points is visualized and can be queried, right? So we're able to handle some very, very large data sets. It's not super fast, but it will work on a laptop, right? And it's not a particularly special laptop. So other obstacles are, Dale Harris mentioned this at the start, coordinates. You have data sets in a mixture of local mine grid coordinates and geographic or UTM coordinates. You might have different vertical datums. So, you know, depending on when your drill holes were drilled, they might be, you know, on one datum and later ones might be on another datum, all sorts of things like that. So sorting out the coordinates is a big thing. Again, I had a client where they had to bring a guy out of retirement to tell them what the local to UTM transformation was from their local grid to the you know, to actual UTM coordinates, so we could actually register some of the data that they had. You have database issues where you've got 300 million data, geology codes in your database. You've got either insufficient or non-existent metadata, which means that you can't properly use the data that you have. You've got poor drill hole collar locations. So in particular, the Z of the drill hole is often, historically that wasn't necessarily recorded. And just because you have a drill hole collar up in the air doesn't mean it's wrong. It could mean that someone came along and dug a big pit there in the intervening 30 years between when it was drilled and when you were looking at it. So, there's a lot of things that you have to sort out with your drill hole locations. And you have databases that are a mixture of good and bad data, and geochemistry would be a classic where you have stuff from different labs with different detection limits, and it's all just smashed together into a single database, or magnetic susceptibility database. I've never seen a good one yet, where we send the fieldies out to do mag sus measurements and they don't know the difference between 10 to the -3 or 10 to the -5. And again, it's all just in the same database, absolutely useless. You can't do anything with it. All you can do in that situation is get rid of the data that you can't trust, that you're not absolutely certain about, and work with the good stuff. So another obstacle is just poor representation of some data types. Like it's very common to see, say, seismic data imported as images, just pictures, where you can't change the color scale, or you're stuck with whatever visualization the person that produced the image has come up with. And a lot of software doesn't really handle geophysical data very well, particularly the sort of stuff that has non-uniform cell sizes in the models. So a lot of them have increasing cell size with depth, and a lot of software doesn't handle that. So I still very commonly see people looking at, say, geophysical section data, as shown at top right there, where they've just taken the model, which has got increasing cell size with depth, and all they're able to do is visualize it as a bunch of points. And they're supposed to be interpreting features from that type of presentation. In reality, what it should look like as a proper 2D section shown at the bottom is exactly the same data. And I'd much rather be interpreting the one at the bottom, right? So what do we need in 3D visualization? We need the ability to import all the common data types, and there are a lot, all the different geological data types, and then there are the niche areas of geochemistry and geophysics, which have their own formats, and remote sensing. We need to be able to visualize, all the multidisciplinary data that we've collected. We want to see a whole bunch of different presentations, so full 3D, section views or slices, plan views. We want to be able to look at the statistics of the data. We want to visualize data down hole, so it might be core imagery or geophysical logs or whatever. We want to be able to do operations on or between those data sets. So if we have a bunch of properties on a geochemical database, we want to be able to calculate alteration indices and things like that. We want to have links to the niche software. So in geochemistry, that would be iogas, say, like a direct link between whatever 3D software you're using in iogas, or direct link between the software and the geophysical modeling code, so that you can properly integrate your interpretations. We want to be able to add interpretations, digitize things in our view, or on our sections, or on our models, create new objects, and that to be done either manually or automatically. And then we want to be able to do various types of data analysis, which I'll cover a few of later in the talk. So why do we need it? Deep exploration requires a good, strong 3D understanding of the geology. We might want to do integrated interpretation of our data. That's another good reason we need it. The whole is greater than the sum of the parts. That was said by Aristotle, who's shown at the top right there. So it was 2,000 years ago. He was on the money, or longer, probably. We might want to do prospectivity analysis or targeting in 3D. So we call it a mineral potential index, but it's basically a targeting thing. We might want to produce inputs for machine learning exercises. They're becoming more common these days. We call that feature engineering. It's producing the input layers, which are numerical realizations of the targeting criteria. So they're whatever targeting criteria you come up with, you've got to somehow represent that as a property in your model, or a layer in your model that you can put into the machine learning or targeting exercise. And another common application of this is geotechnical hazard assessment, which is very like targeting, only you're predicting the likelihood of a rockfall or something instead of the likelihood of a mineral deposit. So the type of objects we're visualizing in 3D points, that'll be soil geochemistry, gravity data, desurvey drill holes, structural, surface structural data. We have curves, which are geological boundaries on maps, infrastructure, geophysical data, like a line database from a geophysical survey. We have surfaces, which are horizons and faults, your DEM, which is in every single project you'll make, and other interpretational objects like EM plates. We have cross sections, so some types of geophysical data are inherently a cross section, like 2D seismic, but you might just have also geological cross sections. In drill holes, we have lithology assays, core photography, continuous and interval logs, geophysical logs, petrophysical data. Imagery could be air photo, maps and sections, remote sensing data, and 3D block models will be geological models or geophysical models. And then you might have the same thing, but on an irregular grid where the cell sizes are arbitrary, or cell sizes and shapes are arbitrary, and that's sort of geophysical models and stratigraphic grids or geologic grids. And the image at bottom right there shows an example of a faulted stratigraphic grid. And this is a particular type of data structure. This data sitting in this grid, it would know that this unit here on this side of the fault was the same as this one on the other side of the fault. It understands topology. And the top image there is just showing a 2D seismic section, which is not a straight line, it's a curved path, often shot along roads or something like that. And if you want to avoid introducing distortions into your data, you don't want to project that onto a flat plane, onto if you project the curved parts of that line onto a flat plane, you'll introduce distortions. The types of visualizations, point data, you could display it as points of different color or size, but also as vectors or structural tablets. Curves might represent contours, structural form lines, digitized interpretations. Surfaces could be grade shells or geophysical isosurfaces. Drill holes could have lithology, geophysical logs, etc. Imagery, the sort of things we want to do are drape imagery on other objects, apply transparency, display multi-band imagery in a single image, like ASTER data, where you might have a particular combination of bands that will show you particular things you're interested in. So you want to be able to display multi-band imagery. Block models, we want to visualize them as slices and things like ISO values and ISO surfaces, and the same with the irregular 3D models. So it's now possible. There's lots of different software packages that will import and visualize a huge range of different types of data. You can gain a lot just by bringing all your data together into one visualization, but you can gain even more by interpreting it all together in the 3D environment with a team of experts in the various types of data. So it's not a sort of solo effort. It's not, enough to like put a magnetic image in your project and say, yeah, I used the magnetics, because that's, a very token effort to just be looking at a single image of magnetic data and not, squeezing the last drop of juice out of it. And that applies to every single data set that you would put in your project. So if you want to do anything quantitative with your data, you have to worry about quality control, and it's absolutely the least sexy part of the whole process, but absolutely essential. It's very time consuming. It costs money just because it takes a lot of time. But if you want to do anything quantitative with it, it's the old saying of rubbish in, rubbish out, right? You've got to have good data to start with. And even if that means just throwing away the stuff you're not sure about, that's probably, I think, better than leaving it in there. So just some examples of types of visualizations and useful visualizations we can do now, like a lot of software can do. These are just some drill holes with a few wedges off here. And then here's a geological horizon. And one very useful thing we can do is just calculate the distance from any point on that surface, that green surface, to the nearest drill hole. And that shows us where that surface, immediately shows us where that surface is constrained by drilling, and where it's not. So where it's pink, it hasn't been intersected by the drill hole, basically, in this case. So, or it's a very long way away from the nearest drill hole. So that's a very effective way of sort of getting a reliability of, or uncertainty of your geological surface. And you can do that in 2D on a surface or in 3D on a block model. So that's just doing exactly the same thing in 3D. We're calculating the distance from every cell of that block model to the nearest drill hole. And blue is good. That means you're close to the drill hole. Pink is bad. You're a long way away. When you have multiple properties on the same block model, you can start getting fancy and doing things like co-rendering, where you're displaying two properties at once and you're looking at a mixture of two properties. And this might not be the best example ever constructed, but here I'm visualizing the geological block model and the distance to drill holes on in the same view. And that's just a 50-50 mix of geology and distance to drill holes. And you can see both data sets. You can see the distance to drill holes image here. You can see one of your geological contacts coming down here. With 3D block models like say 3D seismic data, you know, it's common to just visualize them as slices like this. One will be inline and then cross lines and horizontal slices through your 3D block. But we also have, you know, fancy visualizations like fence probes, where you can just digitize an arbitrary section through that 3D block model. Might be along a line of drill, not a line, a curved, you know, a random assortment of drill holes. So you can actually extract the data right on your drill holes and get the section that you want. So they don't have to be straight. So in terms of some examples of analysis of the data in 3D, we can visualize any property on any object as a histogram. So we can look at the statistics of that property, whatever it is. This might be density or whatever. This is actually alteration index. Sorry, Ishikawa alteration index. And you know, some software will let you even do that on subsets of a particular object. So you might have a particular region of interest, and you can just analyze data from just a subset of a surface. You can do cross plots. So this is titanium versus zirconium cross plot, where the colors represent different lithologies. So we're, you know, presenting quite a lot of data here in one plot, and you can do these cross plots in 2D or 3D. You can do 3D GIS in some software. You can do 3D GIS queries on your data. So this is showing a set of geochemical data, and the yellow points here on this image here, down here, are the ones where the potassium assay is greater than 3%. Right, so we're just looking at a subset of the data. This is showing the same thing, but now we've plotted a few faults on here, and now we're showing in yellow the points that are within 25 meters of those faults. So it's a proximity query. This is a shell query where you're showing only the points. The points in yellow are the ones within the ore body wireframe. So you can give it any surface and say, show me all the points inside this closed surface. This is a trend query where you've got a surface there, and we're only looking at the points where the dip of that surface is 50 degrees. We haven't specified a direction. We're just saying, just show me the geochemical data on that surface where that surface has a dip of 50 degrees in whatever direction. And this is another kind of, well, this is a curvature query where we're highlighting here the data that's sitting in depressions in that surface. So it could be domes, or it could be inflection points, whatever. you can be quite complicated. We also have intersection queries. So the yellow points here are the places where those drill holes intersect that surface. So there's quite a lot of, and any one of these queries we can view as a table of data. So we can view it, in the 3D viewer, but we can also see the data that corresponds to those queries. And all those queries can be combined with Boolean operators. So you can say, show me where potassium's 3% and we're within 25 meters of fault and whatever. And, you can construct pretty complex queries that way. So we can view data on stereo nets. So the bottom image there is a set of surface structural data where the structural measurements are displayed as oriented tablets in 3D, showing the dip and dip direction of the measured dip and dip direction. And that's shown on the stereogram, the same thing shown on the stereogram at the top. So this is inside the 3D visualization software. And you can do queries on that stereo net. So we can draw, it's probably pretty hard to see, but there's a blue polygon drawn here where we've just subsetted a bit of data by drawing a polygon around it. And the bottom image there shows the distribution of those points that we've selected with that polygon in 3D on that data. So those red dots are the actual locations of the points that we've selected on the stereo net. We can make, if we're doing geostatistical analysis, we can make variograms. We can apply scripts to data, as I mentioned earlier. You have geochemical data, you can calculate alteration indices, you can change the units of geophysical data, get everything in your project in the same units. It's a really great idea. If you want to integrate it, you can do other things that are used for, more conventional targeting, like pairwise comparison and contrast curve computation that are used for, assessing which criteria are actually important for making a prediction about whether or not mineralization is likely to occur. So those are sort of specialized topics. I won't go into them. So an idea we use at Mirror Geoscience, and which we stole from the petroleum industry, is the Common Earth model, which is an explicit quantitative model of the Earth, which is consistent with all the available geoscientific data, which you can test by drilling and which you can revise as more data becomes available. So sometimes putting all your data, or getting all your data to agree with one another is really easy. Other times it feels like you're, crucifying yourself, and it's extremely difficult and, character building. So in the Common Earth model, every cell or voxel of that model has a whole range of data. It has lithology, it has alteration, it has physical properties from geophysical inversions like density and mag sus and conductivity. It might have geotechnical parameters. It might have targeting criteria, which are these, numerical realizations of your targeting criteria, like distance to particular contact or something like that might be in there. So the framework for that Common Earth model is a robust 3D geological model, which we tend to build up by integrated interpretation. And in integrated interpretation, I guess we say that every component of the model that's not a direct observation from drill core or outcrop is interpretation. And the only way of exploring away from the drilling or outcrop within the sort of 3D volume is by geophysical data, like it or not. It's our only way of apart from direct measurement, it's our only way of exploring in 3D. To create 3D model is a multidisciplinary, interpretive and iterative process. So you don't just put everything together and come up with a model and it's fantastic. There's usually a lot of soul searching and head scratching and several iterations of the model building until you get it right, or till you get something that does basically agree with all your data. And this approach helps to reduce the ambiguity in your interpretation, and ambiguity exists in all kinds of data. It's well known that geophysical inversions are often non-unique, but a lot of geological interpretation is also non-unique. So by combining everything, you're taking the best bits of all the data sets, or the last little vestige of information in every data set, and combining it to come up with the best possible model. So the way, some ways of deciding between all these infinite number of possible solutions that we might have, or models that we might have, one very effective technique is to narrow down the range of options using prior knowledge. So there's geophysical prior knowledge. We know, for instance, that conductivity has to be positive, or from petrophysical data that we might have certain, that a certain unit has certain bounds on its physical properties. We might know that particular geological horizons have been intersected in a particular location by drill holes, and they have to be there. They can't be somewhere else. They have to be where they're intersected by the drill hole. We can use logical prior knowledge, which is just looking for a simplest possible answer with as little detail as possible, which is sacrificing resolution, but stops you over-interpreting your data. And we can use geological prior knowledge, like what the character of the model is. Do you expect an interface to be gradational or sharp? So is it a faulted boundary, in which case it'll be nice and sharp? Some idea of the sort of things that you're trying to, how big things you're trying to model are likely to be. You can use structural data, etc. So these are just some examples. And the sort of workflow we'd normally follow in integrated interpretation is to import the data and QC it, and that can be done prior to import or after. Probably, there's a lot of specialized software there for QCing different kinds of data. It's probably better to do it before you bring it in, if you can, although you can do more once you've brought it in. A common thing we do is then develop a cover model. It's amazing how many people don't know much about the cover in their area. It's very important in Australia. Obviously, we've got a lot of cover, and information on the cover can come from drilling, but also geophysical methods like EM and gravity, provide a lot of information on the cover. And even magnetics, sometimes you can see magnetic paleochannels and things like that in the magnetic data, and you know that your cover's got to be a little bit thicker in those areas where you can see the channels. So and the reason for developing the cover model is it's a very useful constraint on the geophysical data. So the weathered material has low density, close to zero magnetic susceptibility. It'll be a good conductor in the EM, etc. So it's a useful constraint on that, but also in interpreting your geochemical data. Is this sample in the cover or is it in the basement? For sampling that's been done prior to development of that model. So then we might move on to a structural interpretation in 2D of all the geophysical data, and basically just domain it up in 2D, saying what we can see what sort of different regions or domains we can see in the geophysical data, and what they relate to in terms of the known geology. And that would be building up a sort of 2D interpretation. Then we can create a starting 3D geological model, which will have a cover. It'll be constrained by drilling and outcrop. We can start putting contacts in there from the structural interpretation. If we don't have any information on the dip of those contacts, we can assume for starters that they're vertical and fix it up later as we get into the modeling. But you can, you build up a very simple, initially a simple 3D geological model, and then really tweak that geological model by geologically constrained modeling and inversion. I'll just note here that when you're doing this sort of geophysical interpretation, when you don't have much geological constraint, then if two different geological units don't have any physical property contrast, they've got the same density and same magnetic susceptibility. As far as geophysics is concerned, they're the one unit, and you just simplify those two into a single unit. It might be two quite distinct geologies, but physically we can't separate them. Some of the other geophysical data, like EM, can provide structural information. I'll show you a case history of that very shortly. And you sort of go through this iteratively and look at the misfit between the geophysical response of your model. So that geological model that you're building up has got physical properties in it, and you can calculate the the response of that model for various different geophysical techniques. And you look at the comparison of the observed geophysical data and calculated, and where it's not fitting, that's where you know you've got to make some adjustments to your model. So it might not be the entire model, it might just be one part where you've got a contact in the wrong place or with the wrong dip, or there's a fault you didn't know about, or whatever. But you only have to really adjust the part of the model that's causing a problem. Once you've gone through that cycle a few times, you can then populate that 3D model with other data like alteration data, the targeting criteria, etc. And you can easily, once you've made it, it's not that big a deal to come back to it and update it when new data becomes available, like a new survey or tons more drilling or whatever. So I've got one quick case history. This is Cave Rocks in Western Australia, which was a nickel exploration project. So the image on the left is the first vertical derivative of the magnetics, and it just shows a couple of locations. So this is Kambalda, which I'm sure you all know, and the red dots here are known nickel deposits. So there's quite a lot of nickel mineralization around Kambalda. And then we're looking at the next belt over, which is the Cave Rocks stratigraphy. And you can see this big fold here in the magnetic data and this granite here. Cave Rocks, for whatever reason, there's not much nickel mineralization known in there. There's a lot of gold, but not much nickel. And there's a very simplified geological map on the right. And, you know, as usual, the ultramafics are shown in purple, mafics in green, and the metasediments are in grey. And this is a felsic intrusion. And separating the Kambalda stratigraphy from the Cave Rocks strat is this Zuleika shear zone, which runs up the eastern side of Cave Rocks. So we were lucky in this project, we had really good geophysical data coverage. So we had good magnetic data, coverage of Falcon airborne gravity gradiometry. So that's, you know, really good gravity coverage. And we had partial coverage of airborne EM. So I haven't actually shown the airborne EM data, but the yellow lines on this image on the right are the location of the airborne EM survey. So that was a VTEM survey. And you can see just by looking at the magnetic and AGG images that they're complementary to one another. They're showing some of the same things, but they're showing also there are differences between them. And that's the best possible situation where your different input data sets are complementary to one another, and they're all giving you a different sort of angle on the data. If they're all showing you the same thing, you might as well just have one. But if, you know, when they're complementary to one another, that's the best. So this is the information we were given at the start of the project, where that's the AGG image on the left. And this was straight from our client, where this big fold that you can see in the gravity data here has been interpreted as an anticline. So they've drawn this blue dashed line as the axis of that antiform, and the Zuleika shear zone is running up this side of on the eastern side of the Cave Rocks area. So the area we were looking at in this study is in here. We had one cross section just south of the area we were looking at, and this is, I don't know where this came from, but you know, just showing this big anticlinal structure that had been interpreted. So again, greens are mafics, purples are ultramafics. And you can see that it's pretty chopped up. There's not much outcrop in this area either. So it's not, you know, necessarily obvious what's what, but this is, you know, exactly what we were told by the client. We went ahead and started interpreting the potential fields data. So this was done by a bunch of different people all working in parallel, and on the assumption that it was an anticline, and without really doing our homework. And we built up this pretty complicated model that you can see on the left. That's just showing the contacts in the 3D model that was built up. But we started to get some nagging doubts about the model. On the left-hand side, you've got a couple of cross sections. The top one is magnetic susceptibility. It's just a cross section through the inversion. That's right on the running along the fold axis, just in the northern part of the area here. So we're just running through the north-south through this big fold. And there's the that line there that you can just faintly see on the sections is the hinge of the south plunging anticline in the model. And so, and I should say north is at the left-hand side, south is at the right-hand side. And you can see in the magnetic model here that the magnetic, the zone of high magnetic susceptibility crosses that contact. And we've got sediments, metasediments on one side and mafics on the other. But the magnetic inversion is sort of saying we've got magnetic material on both sides of the contact. And in the density inversion, this is an unconstrained inversion, but still, you know, we get this very clear dipping interface, dipping to the north, and the hinge of that anticline is dipping to the south, plunging to the south. So we didn't really like that. In parallel with the potential fields interpretation, we started looking at the airborne EM data, even though it only had partial coverage, so it wasn't sort of a primary data set. But with airborne EM, you quite commonly see these nice, if you've got thin, like tabular dipping conductors, like graphitic shales or massive sulfides, they produce these quite diagnostic looking anomalies in the airborne EM. If the conductor is just vertical, you get a double peak response. Both peaks are the same amplitude. When it starts dipping, the symmetry of that response becomes asymmetric, and the bigger peak is on the down dip side. And just as an example, so that's in theory, that image at the top, or those plots at the top are in theory, but this is a real example, just showing one of these anomalies on the extreme eastern end of this profile here. And you can see it's got the nice double peak. The bigger peak is on the western side, so that conductor is dipping to the west. Okay, and at the bottom here, I'm just going to show you and mention for just for reference, that's the conductivity depth image from that same data. And the only thing you can really take away from that is the layered, the cover, the conductive cover, which is flat lying, is the only meaningful thing in that data. It's a sort of layered approximation, this type of transformation. And anytime the geology is 3D, it'll start to stuff up and produce artifacts. And all this stuff in here doesn't reflect the true geometry of what's going on in the basement at all. Okay, so that's basically uninterpretable. This section is uninterpretable in this type of visualization and processing. What we did was go through all that data. We picked all those anomalies that we could see, like this one here. And without even doing any interpretation, we just said, which way are those things dipping? Are they dipping to the east or the west? And then plotted it all in 3D. So plotted those picked dips as structural tablets. And you can see by looking at this, so we're looking to the north here, that all the ones on most of the ones on the western side, sorry, are dipping to the east. And most of the ones on the eastern side are dipping to the west. And that's starting to not look like an anticline where we'd expect this geometry. It's looking like this. Okay, so we had this misfit between the potential field data and the sort of geological model, and this evidence from the EM that maybe we were actually looking at a synclinal structure here, not an anticline. And we went back and remodeled it. We rebuilt the whole model as a syncline, which is shown right there. And then we get much better agreement between the geophysical inversions and the model. So this is a contact from your magnetic inversion, and there's the hinge of that north plunging syncline there. So at least this interface here is parallel to this one. It's not on that contact, but it's parallel to it. And there's very good agreement between the gravity data, so the mafics to the south and the sediments to the north. We've got good agreement between that north plunging syncline, sorry, and the gravity inversion as well. So everything starts to look, everything just fit better with a syncline rather than anticline. And right at the end of this, I went back and there wasn't much outcrop in the actual area we were looking at, but just south, I finally looked at the GSWA regional geology map, and this is sort of the very southern end of this same fold that we're seeing here. And back in 1988, those guys had mapped it as a syncline. And somewhere along the line, in company reports or something, that had been turned into an anticline, and one person had just copied the results from the previous report into another report, and so on, and eventually it had become an anticline. And what was happening, they drilled 35 holes here, and only 2 of them had actually hit the basal contact of the ultramafics, which is where they were looking for their mineralisation. And when you think about it, what's happened, they've had their structure upside down, and instead of drilling across dip, they've been drilling down dip and never hitting the contact. Right? So it was just a really interesting example of putting everything together. Now I'm going to show you a very, very quick, I'm probably going to go slightly over time, sorry, but a very, very quick example, sorry, of 3D visualization. And, you know, despite the white hair here, I'm not unknown for taking wild risks, and doing live software demos is one of them. So, you know, I should know better, but I'm going to give it a shot. So this is basically an almost empty project. This is Geoscience Analyst, which is our, you know, one of our software packages. All the import stuff I'm going to show you is all part of the free viewer that you can just download and use for free. If you want to do anything serious with any data in Geoscience Analyst, you've got to pay a small amount of money. And I mean, like it's $1,000 a year for a license. It's not expensive. So if I just pop up this window, I'm just going to put some data in here. Sorry, I better. So I'll just drag and drop an ER Mapper grid file in here of topography. So that's not looking very 3D yet. I'll just turn the colors on. So that's our DEM as a grid. I can right click on that, go to create, surface from data, and I'll just call it surface, turn my grid off. And I've turned that grid into a 3D surface of the topography. This is Manitoba in Canada. It's very, very flat. It's like Western Australia. So we need a bit of vertical exaggeration to see what, you know, there is actually something there. And I'll color it by Z. There's your topographic surface colored by elevation. I'm then going to import an air photo. So this is just a geotiff. Again, just drag and drop into the window here. Takes a couple of seconds. So now I've got an air photo underneath my surface, and we can drape that air photo onto the topography very easily. So if I go to visual parameters and actually choose the surface, go to visual parameters, we can paint that image onto the topography. And if I go back here, now I've got 2 of them. I just turn off the actual grids or the original images that we brought in. And this is Flin Flon in all its glory. I'll just look down on it in plan. You can see that it would be a lovely place to live. It's got these lovely tailings ponds right next to the town. Plus, you know, it's extremely nice in winter when it's -35. So it's got a lot going for it. What I will bring in next is just a geological object. So this is just a DXF, which is a common interchange format for surfaces. Just drag that in, and I'm bringing in a fault. So there's a whole bunch of faults. Sorry, they're all colored the same color. I'm just going to turn a few off so that we can actually see one. We could change the color of that to something we can actually see. There's the fault. I'm next going to bring in the geology model. And this is just, you can import this directly from the Leapfrog model, but I'm just going to bring it in as a geoscience analyst object. And there's our like 3D geological model that had already been built. This has got the air, because it's a geophysical model, it's got an air layer in it. So we can go to that geology model here and choose the lithology there, and just turn off the air layer, and then we'll be able to see our air photo sitting on top of the geological model. So we're viewing it there as a volume. We can also go back to the visual parameters here and turn on a few sections and turn off the volume, and then that's probably the more sort of presentation you're more used to, where you're just viewing a few east, west, north, south and horizontal sections through your model. And it looks funny because we've got a 5 times vertical exaggeration because we're in Manitoba. So that's the geological model. I'll just bring in some EM data. And again, I could import this from the raw files, but I'm just bringing it in. It comes in faster in the native format. But if I turn that on, I've got some EM data there, just showing as stacked profiles on the lines draped on the topography. So that's your actual raw data. I've got a plate that's been interpreted from that data. So I'll just import that and turn it on. And then there's my interpreted plate. You can see it in cyan there. That's the interpreted plate. So now I'm going to turn the data off now that we've seen where it came from. I'll just turn the I actually won't turn the geological model off yet. I'm going to bring in next a magnetic model. It's just a UBC mesh. This is the sort of format that comes straight from the geophysical inversion software, but it's just a very basic 3D format. And I'll just drag those two files in, and I will turn the geological model off just temporarily. So there's my, and I'll turn the fault off, wherever that is here. So there's my volume from my geophysical data set. And this is magnetic susceptibility. It's coming with a weird name, but I can go to my visual parameters and turn on some sections. Oops. Go back to the viewport, and we're starting to see, you know, our areas of high magnetic susceptibility in our model. So you can view what I'll do next is just transfer the data from that UBC model that we just brought in onto the geological model. So this is a really powerful feature of this kind of software, is just transferring data. So the source data is going to be the UBC magnetic model and the magnetic susceptibility data. And the target is going to be the geology model. So I'm going to copy that magnetic susceptibility data across to the geology model so it can be viewed with the geological data. And I'll just say okay here. I'm just doing it by nearest neighbor. Turn off my UBC model and go back to my geology model. And you can see in the tree here that the geology model now has 3 properties. It's got a magnetic susceptibility property as well as the other ones that it had. So I can turn the geology model on. I might need to just rescale the plot. Oh, I haven't turned it on. That's why it's not showing. There's the magnetic data on the geology model. And then I'm going to go from here. We can, instead of visualizing this as just slices, we can do things like calculate isosurfaces and show ISO values and things like that. I'll just show some ISO values. So I'll just show a susceptibility ISO value. And I think that one's a good one. Just showing the areas of high magnetic susceptibility in the model. And they're shown here, right? So it's like an isosurface, just enclosing all the material of a certain magnetic susceptibility and above. You can see that our plate here that we've made, I'm very nearly done. The plate here that we've made is also a magnetic body, so that might be a great exploration target. If I turn this thing off, I'm going to try and drill this target. If I go to the drill hole designer, I can create a target, and I can just pick a point on that plate that I'm going to aim for with my drill hole. So you can see that yellow box on there. That's my drill hole target. And I'll just create it. It's called new target. There it is. And then I can go to the drill hole designer and say, I'm going to design some drill holes from target to surface. My surface is going to be my topographic surface. My target is going to be that new target. I'm going to give it a bit of slack so that thing is dipping at a particular dip and dip direction. We don't want to intersect perfectly perpendicular to that, that target. We can give it a bit of slack. I'll just give it 5 degrees just for fun. And I'll go plan the drill hole to be 50 meters past the target, which is good for your geochemical reasons as well as geophysical. And then if I suggest paths, it'll take a little while to calculate. But now it's given us a whole bunch of, just move this out of the way. It's given us a whole bunch of possible drill holes, drill hole collars that would intersect that target within that tolerance that we gave it, that 5 degree tolerance in azimuth and dip. And if you go and look at where those collars are, if I go and plan, then you'll see that they're all in the middle of Flin Flon town. So you might get away with it, Flin Flon, drilling a drill hole in the middle of the main street, but you know, you probably need to go back and replan your drill holes. And if I bring this thing up here, I think I lost I'll just say use shortest path, and it will pick just the shortest drill hole path of that the bunch that it's created. And now we should have just one drill hole. Maybe I'll just have to say shortest path, create. Now I've got to close that. Now we've just got one, zoom out, we've just got one drill hole that goes from surface through our target. So I'm going to leave it there. That was a bit rushed in the end, but we made it. Okay, thank you very much.